So, are we all going to be torn apart? It's a big question, probably the biggest. The end of everything, not just us, not just Earth, but the whole universe. For a long time, we had a couple of main ideas about how it would all go down. But then we discovered something strange, something that threw a wrench in the works. And that something opened the door to a new and frankly terrifying possibility. A possibility called the Big Rip. To get there, we have to start with the old story. The story of gravity. For most of human history, gravity was the undisputed king of the cosmos. Isaac Newton figured out its rules on Earth and saw they applied to the planets too. Gravity pulls, it brings things together, it makes apples fall, and it keeps the moon in orbit. It was the great organizer. Then came Einstein. He showed us that gravity wasn't just a force, but a curvature of space-time itself. Massive objects bend the fabric of reality, and other objects follow those curves. But the basic idea was the same. Gravity pulls. It's the cosmic glue holding everything together. Stars, galaxies, clusters of galaxies, all of it held in the firm grip of gravity. So, when we learned that the universe was expanding, that galaxies were flying away from each other, the obvious question was, will it stop? Edwin Hubble saw the galaxies rushing away in the 1920s. The universe started with a Big Bang, a moment of incredible expansion. And ever since, it's been growing. But gravity is always there, pulling back, trying to slow things down. This set up a cosmic tug of war. On one side, the leftover momentum of the Big Bang pushing everything outward. On the other side, the collective gravity of all the matter in the universe pulling everything inward. The fate of the universe depended on who would win. This led to a couple of main scenarios. The first one was the Big Crunch. If there was enough stuff in the universe, enough matter, and therefore enough gravity, the expansion would eventually slow down. It would grind to a halt. And then it would reverse. Galaxies would stop moving away from each other and start moving toward each other. The universe would begin to contract. Over billions of years, it would get smaller, hotter, and denser. Everything would fall back together, culminating in a final fiery singularity, the opposite of the Big Bang. A cosmic nabgib. The end. The other possibility was that there wasn't enough matter. If gravity's pull was too weak, it could slow the expansion down, but it could never stop it completely. The universe would just keep expanding forever, but it would be a sad, slow decline. This is often called the Big Freeze or the heat death. Galaxies would get farther and farther apart. Stars would eventually burn out. The universe would become a cold, dark, and empty place. A vast graveyard of dead stars and black holes. A quiet, lonely end. For decades, this was the debate. Crunch or freeze? It all depended on a single number, the density of the universe. Was there enough mass per unit of volume to make gravity win? Astronomers spent years trying to measure it. They counted galaxies, they estimated the mass of stars, they looked for all the stuff they could find. And the numbers always came up short. It looked like gravity was going to lose. The Big Freeze seemed to be our fate. But there was a wrinkle. Astronomers noticed that galaxies were spinning faster than they should. The stars on the outer edges were moving so fast they should have been flung off into space. The gravity from the visible matter wasn't enough to hold them in orbit. There had to be something else there. Something we couldn't see. They called it dark matter. This invisible substance had gravity, but it didn't shine or interact with light. And there seemed to be a lot of it, way more than regular matter, so the search was back on. Maybe if you added up all the regular matter and all this new dark matter, there would be enough to cause a big crunch after all. The cosmic scales were tipped back and forth. For most of the 20th century, the end of the universe was a story about gravity and matter, or a story about a battle between expansion and contraction. Then, in 1998, everything changed. Two separate teams of astronomers were working on a project. They wanted to measure the expansion rate of the universe more precisely. A specific type of exploding star, a type I of supernova, as a kind of cosmic yardstick. These supernovae are great because they all explode with roughly the same brightness. So if you see one that looks dim, you know it's very far away. If you see one that looks bright, it's closer. By measuring their light and how much it had been stretched by the expansion of space, they could map out the history of the universe's expansion. They expected to see one of two things. Either the expansion was slowing down a lot, meaning a big crunch was in our future. Or it was slowing down a little, meaning a big freeze was coming. Both teams crunched their numbers. They checked and rechecked their data, because what they were seeing made no sense. It was impossible. The distant supernovae were even dimmer than they should have been. They were farther away than the models predicted. The only way that could be true is if the expansion of the universe wasn't slowing down at all. It was speeding up. Let that sink in. The expansion of the universe is accelerating. This was a bombshell. It was like throwing a ball into the air and watching it shoot up faster and faster instead of slowing down. It broke everything we thought we knew. The tug of war wasn't just between the Big Bang's momentum and gravity. There was a third player on the field, and it wasn't pulling, it was pushing, this mysterious force, this anti-gravity, pushing the universe apart at an ever-increasing rate, was given a name dark energy. And with dark energy, the story of the end of the universe got a lot more complicated and a lot weirder. So what is this dark energy? The honest answer is we have no idea. It's one of the biggest mysteries in all of science. We can see its effects, we can measure how it pushes space-time apart, but we don't know what it is. It seems to make up about 70% of the entire energy density of the universe. Regular matter, the stuff that makes up you, me, and the stars, is only about 5%. Dark matter makes up the other 25%. So we live in a universe dominated by two things we can't see and don't understand. But we have some ideas. The leading theory is that dark energy is a property of space itself. It's the energy of the vacuum. Even in completely empty space, there's a kind of baseline energy and inherent springiness to the fabric of reality. Einstein actually thought of this a long time ago. He called it the cosmological constant. He put it into his equations to make the universe static, to balance out gravity. When he found out the universe was expanding, he called it his biggest blunder. But he might have been right all along, just for the wrong reason. If dark energy is this cosmological constant, this energy of empty space, it has a strange property. As the universe expands and more space is created, more of this energy comes into being. So, the total amount of this outward push gets stronger and stronger over time. Gravity, on the other hand, gets weaker as things move farther apart. So in the early universe, gravity was the boss, but as the universe expanded, dark energy began to take over. And a few billion years ago, it became the dominant force. That's when the acceleration kicked in. The future of the universe now depends entirely on the nature of this dark energy. Is it constant, or does it change over time? To figure this out, cosmologists use a parameter. They call it. It's the equation of state parameter, which sounds complicated, but it's just a way of describing the character of dark energy. It's a ratio of its pressure to its energy density. The value of who tells you what kind of future we're in for. If U equals 1 exactly, then dark energy is Einstein's cosmological constant. Its density stays the same forever. It pushes, but it's a steady, constant push. This scenario leads back to the Big Freeze. The acceleration would continue, galaxies would fly away from each other until they disappeared over a cosmic horizon, and the universe would end in a cold, dark, empty state. A lonely but peaceful end. But what if was is not exactly 1? What if it's a number greater than 1, say 0.8? In this case, the dark energy, sometimes called quintessence, would weaken over time. The push would get less and less powerful. It's possible it could even fade away completely, letting gravity take over again. This could, in a very unlikely scenario, still lead to a big crunch. And then there's the third option. The one that keeps cosmologists up at night. What if we's less than 1? What if it's 1.1, or 1.5, or 2? This seems like a small difference, but in cosmology it changes everything. If WA is less than 1, the dark energy has a new name. It's called phantom energy, and it behaves in a way that seems to violate our understanding of physics. With phantom energy, the density of dark energy doesn't just stay constant as the universe expands. It increases. Think about that. As space gets bigger, the amount of dark energy in each cubic centimeter of space actually goes up. The repulsive force grows stronger and stronger, not just overall, but locally, everywhere. The push becomes more and more violent over time. It creates a runaway feedback loop. More space means more phantom energy, which means space expands even faster, which creates even more space, which creates even more phantom energy. This runaway acceleration leads to the Big Rip. The Big Rip is not a slow, quiet end like the Big Freeze. It's not a fiery, crushing end like the Big Crunch. It is a violent, sudden, and complete disintegration of everything. It's the ultimate undoing. So here's how it would happen. The timeline is speculative, but the physics behind it is brutally simple. The story of the Big Rip is the story of the repulsive force of phantom energy overwhelming every other force in the universe, one by one, from largest scales to smallest. For the next many billions of years, things might not seem too different. The universe will continue to accelerate expansion. But the phantom energy is growing stronger, slowly, relentlessly. The first victims are the largest structures. Sometime around 20 billion years from now, give or take, the repulsive force will become strong enough to overcome the gravity-holding clusters of galaxies together. The Coma Cluster, the Virgo Cluster, all these massive cosmic cities of galaxies will dissolve. Their member galaxies will fly off on their own into the expanding void. Then, the phantom energy continues to build. The target gets smaller. A few tens of millions of years before the final rip, the force will be strong enough to overcome the gravity holding individual galaxies together. Our own Milky Way would be the next to go. The phantom energy pushing from within the galaxy would become stronger than the gravitational pull of all its stars, gas, and dark matter. The beautiful spiral arms would unravel. Stars would be flung out into the darkness. The galaxy would disintegrate into a formless, expanding cloud of isolated stars. The clock is ticking faster now. The end is approaching. A few months before the end, the force becomes strong enough to unbind solar systems. In what's left of our local space, the outward push would overwhelm the sun's gravity. The Earth, Mars, Jupiter, all the planets would be torn from their orbits and sent hurtling into space, no longer bound to their star. The final moments are a rapid cascade of destruction. About 30 minutes before the end, the Earth itself would succumb. The phantom energy welling up inside our planet would be stronger than the gravity holding it together. The Earth would explode. A few seconds before the end, the electromagnetic force, which holds atoms together, is next. The phantom energy would become so strong that it would rip electrons away from their nuclei. All matter would be reduced to a plasma of unbound particles, and in the final fraction of a second, the last fundamental force of nature falls. The strong nuclear force, the most powerful force we know, the glue that holds atomic nuclei together, would be overwhelmed. Protons and neutrons would be torn apart into their constituent quarks. The universe would be reduced to a soup of elementary particles that can't even interact with each other because they are all flying apart at an infinite, or near infinite, speed. And then, the final moment. The rip itself. What happens then? It's hard to even say. The expansion rate would become infinite. The fabric of space-time itself would be torn apart. Every point in the universe would be infinitely far away from every other point. The concept of distance would lose its meaning. The laws of physics as we know them would cease to exist. It would be the end of space, the end of time, the end of reality, a singularity of a kind we can't even properly imagine. It's a dramatic, almost cinematic end, and it's a real physical possibility. So the big question remains, is this our fate? Is the universe fated to experience a big rip? The answer depends entirely on that one number, though. So what have we measured? What does the evidence say? Scientists have been working tirelessly for the past couple of decades to pin down the value of WOO. They use data from the cosmic microwave background, the afterglow of the Big Bang. They use observations of how galaxies are clustered together, and they use more and better supernova data. All of this information is fed into our cosmological models to try and constrain the value of WID. The results? Our best measurements to date show that was very, very close to 1. The Planck satellite, one of our most precise instruments for measuring the early universe, found a value of 11.03 plus 0.03. Let's break that down. The central value 1.03 is in the phantom energy range. It's less than 1. That would mean the big rip is on. But look at the uncertainty plus 0.03. This is the margin of error. It means the true value could be anywhere between 1.00 and 1.06. The value of 1, the cosmological constant that leads to a big freeze, is sitting right there inside the margin of error. And in science, if your measurement is consistent with a simpler, more well-behaved number, you usually lean toward that one until you have much stronger evidence to the contrary. The idea of a constant, unchanging dark energy is simpler than the idea of a phantom energy that grows stronger over time. So based on the current evidence, we can't say for sure, but the data is perfectly consistent with the Big Freeze scenario. There is no strong evidence pointing to a Big Rip. Most cosmologists today would bet on the Big Freeze. It remains the leading, most conservative theory. The Big Rip is an outlier, a possibility that lives in the margins of our measurement errors. There are also theoretical reasons to be skeptical of the Big Rip. Phantom energy is just plain weird. It has negative kinetic energy, which is a concept that gives physicists headaches. It suggests that the vacuum of space is unstable, which could lead to all sorts of other problems. Many physicists feel that phantom energy is unphysical and that a deeper theory of quantum gravity will eventually rule it out. It might just be a mathematical oddity that doesn't exist in the real world, but we can't be sure. our measurements could get better. The next generation of telescopes, like the Euclid satellite or the Vera C. Rubin Observatory, will measure the expansion of the universe with unprecedented precision. They might narrow down that margin of error. They might find that that is definitively 1.05. Yeah. Or they might find that it's definitively 1.00. Or they might find that it changes over time. We don't know what we'll find, and that's what makes it so exciting. It's important to remember that all three major scenarios for the end of the universe are still on the table, even if their probabilities have shifted. The Big Freeze is the current frontrunner, a universe that expands forever, becoming increasingly cold, dark, and lonely. All distant galaxies will eventually accelerate away from us so fast that their light will never reach us. They will disappear from our view as if they never existed. The night sky for any future civilization will be empty except for the local gravitationally bound stars. Eventually, those stars will die. The universe will fade to black. The Big Rip remains a dark horse candidate. It's a possibility if the nature of dark energy is more exotic than we think. It's a violent, universe-shattering end that depends on who being just slightly less than one. It's unlikely based on what we know now, but we can't rule it out. And what about the Big Crunch? It seems like the least likely of all, given the accelerating expansion, but we can't entirely dismiss it either. What if dark energy isn't constant? What if it's a dynamic field that could decay or even change its nature? Some theories propose that dark energy could flip from being repulsive to being attractive in the distant future. If that happened, the acceleration would stop and gravity would take over, pulling everything back into a final Big Crunch. Some even speculate this could lead to a Big Bounce, where the crunching universe ignites a new Big Bang, starting a new cycle of cosmic existence. In the end, our fate is tied to the nature of a substance we have only just discovered and do not understand at all. Dark energy holds the key. Understanding it is one of the most important goals in modern physics. So, is the universe fated to experience a Big Rip? The honest answer is probably not. Based on the best evidence we have today, a long, cold, quiet Big Freeze is the more likely outcome. But we're not certain. The universe has surprised us before. The discovery of dark energy itself was a complete shock. There could be more surprises waiting for us as we look deeper into the cosmos. The story of the end is not yet written. We are detectives, piecing together clues from the light of distant stars. The Big Rip is one possible ending in our book of cosmic futures. It's a terrifying, mind-bending idea that pushes the limits of our imagination and our physics. And whether it's our ultimate fate or not, the fact that we can even ask the question, that we can conceive of such an ending and search for evidence for or against it, is a remarkable thing. It's a testament to our relentless curiosity, our drive to understand our place in the cosmos, from its fiery beginning to its final unknown end.